not be in Atlantic Shores.
That's fair. All right. So, is there a home field advantage in baseball? In 2007, the home team won 54.26% of 2,431 games. Is this due to natural sampling variability, or is there evidence that there really is a home field advantage? So this page is just set up to walk you through the process. So the hypothesis, basically in words, we're going to assume there is no advantage. And P is going to be the proportion of games won. So our null hypothesis is going to be that P is equal to 0.5. Because obviously there's home and away. So we're assuming that there's no advantage. The alternate hypothesis is that P is greater than 0.5, which would indicate home team wins more often. Which would mean a home field advantage. All right, so model, we look at the conditions. So, independence. This would be roughly true because one season would be similar to another. As far as randomization, it's not randomly selected because obviously we're looking at all home field games or all home games. But it should be reasonably represented. As far as the 10% condition, what we're looking for, obviously this is all the home games, so you can safely assume it's 50% of the games that year, but we're looking at less than 10% of all games ever played. And then success failure, NP and NQ would be 2,431 times 0.5 for both, which is going to be 1,215.5, which is both greater than 10. So it meets the conditions for a normal model. And the one prop Z test. So then the mechanics is where we actually do the math that goes with this. So the mean, or P0, is 0.5, which we get from the null hypothesis. The standard deviation of P hat we have to find, which is the square root of P hat Q hat over N, or PQ over N. So 0.5 times 0.5 divided by 2,431. And that would be 0.01014. So then we can use the one prop z-test. I'll give you this so you can plug it in. So it'll be the one prop z-test of 0.5. Then it'll be the 0.5426 times 2431, which you can either multiply ahead of time or you can just type it in like this and it should change it. Then 2,431, and then we're looking for greater than P0. So that's just a select from the options. So looking at a normal model, obviously the mean would be 0.5. We care about the 0.54, blah, blah, blah. So I'm looking at the area to the right, which is why it's the greater than option. The one prop z-test. Stat test, I think.
Okay.
Or it might be second stat test, I don't remember. Huh? It may want you to multiply those numbers first.
It multiplied for
0.5426 times 2431.
So it's one prop z-test.
Yeah.
Is it calculate or draw?
Calculate. Try draw and see what happens.
Hold on. Stack test. One prop z-test.
Make sure you're in one prop z-test and not z-interval.
Z-test. So 0.5. 0.5426 times 2431. 243. And then less than or greater than PO, right?
Yeah.
Keeps it here. It can't. I did this right, right?
Okay. It doesn't like the decimal. So for the x value, when it multiplied it, it had a decimal. I took the decimal off and it's fine. So we're looking for this z value here. And then ultimately we're going to use this p value here, which is like that. So Z was like 4.2, right? So then P of Z greater than or equal to 4.20. What was the P value that was given to you?
The P value was
The one that was like right under Z.
1.3.
It was like times 10 to the something, right?
It's 1.345217 e negative 5.
Oh, I just have the wrong number on my paper, that's why. Okay. Alright, so then the P value at that is, it was like point 0.00001 or something like that, right?
Which one?
The P value that you just got off the calculator, that number. It was like 1.3 e to the negative 5, right? Yeah, so that number basically means that a high percentage of home team wins is highly unlikely to be a sampling error. So when we conclude, basically a number that's really, really small like that is going to end up telling us that, in conclusion, a p-value of less than 0.00, well, really less than 0.001, but yeah, a p-value of less than 0.001 in general, but obviously our number was less than that, says that if there was no home field advantage and the true proportion of home wins was P is equal to 0.5, then an observed value of 0.5426 or larger, okay, that's what we started with, would occur less than 1 out of 1,000 times. So then the key part here that we really care about, so I'm going to put it in a different color. A p-value that small would cause me to reject the null hypothesis and yes?
I'll call you back.
Okay. and shows that there appears to be enough evidence of home field advantage and then we could find the confidence interval, but basically, to wrap it up, if we create a 95% confidence interval with this data, we get 0.52277 and 0.56238 as the interval for the true P of home team wins. So you just find that the same way you've been finding the stuff in the other section. Now I'm curious what she called for. I always hate that when somebody calls you and it's like, I'm gonna call you back. It's like, oh gosh, what is it? Thanks. All right, so write the null and alternative hypothesis you would use to test these situations. So all we're doing is writing the H0 and then the HA for this particular problem. So we field test a new flavor soft drink, planning to market it only if we are sure that over 60% of the people like the new flavor or like the flavor. So our null is that P is equal to 0.6. So do you think this would be not equal to, less than, or greater than for the alternative hypothesis? Yep, greater than. And this would be a right tail test because it's over 60%. 20% of cars of a certain model have needed costly transmission work after being driven between 50,000 and 100,000 miles. The manufacturer hopes that a redesign of a transmission component has solved this problem. So the null would be what? And then the alternate would be what? Yep, because a redesign of the transmission component has solved this problem, which would imply that it's less than 20%. And then in the 1950s, only about 40% of high school graduates went on to college. Has the percentage changed? So the null would be what? And then the alternate? not equal to. So it could have gone higher or lower. So this one was a left tail test. I forgot to write it. And this one is a two tail test. All right, so this next one's kind of a multiple choice question. So, the seller of a loaded die claims that it will favor 6. We don't believe their claim and roll the die 200 times to test an appropriate hypothesis. Our p-value turns out to be 0.03. Which conclusion is appropriate, and explain? So, this 0.03 here basically says that the probability of our sample results given, or it is the probability of our sample results given that the null is true. So our null would be to assume that the die is fair. So a 6-sided dice would have a probability of 1 out of 6, which is 0.17. So this is the probability that die is fair. So they're saying that it is a loaded die, meaning that the number 6 is favored. It occurs more times than that. So our alternate would be what? P is what? If it favors something, that means that its percentage would be what?
If it favors something, it means it would be high.
So it's going to be greater than. So greater than 0.17. So this is that the die is unfair and favors 6. So something to remember, when P is low, reject the null. So our p-value is 0.03 and it is low. So reject the null in favor of the alternate. So A and B just don't make sense. So it's got to be C or D. So there's a 3% chance that a loaded die could randomly produce the results we observe, so it's reasonable to conclude the die is fair. Or there's a 3% chance that the die could randomly produce the results we observed, so it's reasonable to conclude that the die is loaded. Which one do you think?
Which one?
Either C or D. Based on what we concluded, which one do you think it is?
C.
But we rejected the null in favor of the alternate, which would mean what? The die is fair or that it's loaded? So it would be D. All right, we'll do the next page and then we'll probably stop for today. Do the last two tomorrow. All right. So, someone hands you a box of a dozen chocolate-covered candies, telling you that half are vanilla creams and the other half are peanut butter. You pick candies at random and discover the first 3 you eat are all vanilla. If there really were 6 vanilla and 6 peanut butter candies in the box, what is the probability that you would have picked 3 vanillas in a row? So this is going back to like a whole unit ago. So the probability that the first was vanilla would be what?
1, 2.
Huh?
1 and 2.
No, because how many vanillas could you have pulled?
6.
So 6 out of 12. And obviously we're not going to put it back. That's gross. So then the next one that you pull for it to be vanilla, you'd have the probability of what?
5 of 11.
And then lastly, you have another one.
4 of 2.
Yep. So what is that probability?
That is 120 over 1,320.
Okay, which is what in a decimal?
Wait, I think I got this. Point 0.09.
0.09. I think there's a 1 after it, but yeah. So I'm going to come back to this in just a second, but I'm going to go down here. So do you think there really might have been 6 of each? So there's a couple different things that we can do, or what we would look at. They're called alpha levels. So alpha could be 0.1. Alpha could be 0.05, or alpha could be 0.01. So these are basically like, kind of like how accurate we want to be, in a sense. So this p-value is not too low. So these kind of decide the threshold where we decide to reject or not reject the null hypothesis. So with this information, it's possible there's 6 vanilla and 6 peanut butter. So then, would you continue to believe that half are vanilla if the 4th one you try is also vanilla? So I would have the same probability from up here, 6 out of 12 times 5 out of 11 times 4 out of 10. Then the 4th one is still vanilla, so I would be on to 3 out of 9. What would that p-value be?
Let's calculate for this one.
0.03. So this p-value is low. So we reject the null hypothesis that there are 6 vanilla and 6 peanut butter. It is possible there are more than 6 vanilla. So a survey investigating whether the proportion of today's high school seniors own cars is higher than it was a decade ago finds a p-value of 0.017. Is it reasonable to conclude that more high schoolers have cars? Explain. So my null hypothesis would be that and your null doesn't always have to be a number. It can just sometimes be words explaining it. So it would be that the percent of high schoolers who own cars has not changed. Then the alternate, that more high schoolers have cars, would be the percent is higher. So, based on this p-value, do you think we're going to reject or fail to reject? Is this low? So we're going to reject. So the p-value is low. So reject the null hypothesis. Meaning that there is enough evidence to conclude the percentage has risen. And since the next problem is a whole page, we're going to save it for tomorrow because I don't know if we would get through it with the time that we have left.